We were looking at the phase domain model of the clock and data recovery circuit with forwarded clock. And we use the linear phase detector, right? The model that we came up with was, or first let me draw the CDR itself. This is the linear phase detector. This is a control voltage which controls the delay. We considered an increment phi d. We first assume that it is locked, okay, and then we consider increment phi d in the phase of the data, or an increment phi c gain in the phase of the clock. This will cause an increment in the control voltage as well as increment in Ck, which is used for data recovery, okay. And you could also add noise from the current sources and so on. We will do that later. So now the model was that you take the difference phi d minus phi ck, that's what the phase detector is doing, and then this gets multiplied by the gain of the phase detector, which is ICP by 2 pi. This will be the gain if you have an alternating input, okay, that is the transition density is 1. In the transition density of random data is half, and it could be in general anything, right? So this gets multiplied by the transition density df. So this is this provides a current ICP, which essentially models the increment in the average output current of the phase charge pump, okay. And this goes into the capacitor C to generate a control voltage increment V control. And now this V control changes the phase of the clock. What it does is it gets multiplied by Kd times omega naught, where Kd is the proportionality constant of the delay line. We assume that this Td is some Td0 minus Kd times V control, okay. So the delay corresponds to a phase when it gets multiplied by omega naught. So you have this, and the output is the additional phase due to the delay line, okay. To this you add the phase of the input clock, and that gives you the phase of the clock that is actually used to recover the data, okay. So this is the phase domain model. So any questions on how we derived this or any aspect of this? Now we can add more things here. For instance, these current sources used to make the charge pump will have some noise, okay. So we can also add that to see what effect they have. I will call it IMCP. So that will be the current noise of the charge pump, okay, effective current noise. Now we have two sources which are switching. We will discuss that. I have modeled the entire noise as an additional current at the output of the charge pump, okay. So now please calculate the following in this. Basically, what is the output here? You can consider the phase of the recovered clock, this is the recovered clock, right? Okay, Ck is the recovered clock. So phase of the recovered clock is the output. So we are interested in the transfer functions, let's say phi ck by phi d, then phi ck by phi ck in, and let's say phi ck by in cp. Okay, please calculate these things. From these we will consider some metrics for the clock and data recovery circuit, some metrics of performance. These will be more important when we go to clock and data recovery without the forwarded clock, because then you don't even have the input clock, right? Obviously you sense that even without knowing it, without knowing the details, that when you do have the forwarded clock, things are easier. Okay, you just have to adjust the phase, but when you don't have it, you have bigger difficulty. Okay. Please calculate the transfer functions. So what are the answers? What is phi ck by phi d? You know the standard forms for negative feedback systems, right? In this case, the forward path has some gain, which is it's normally denoted by G in the control system's parlance. So that is transition density times ICP KD omega naught by 2 pi SC, right? And the feedback term H is just 1. Okay. So now this phi ck by phi d, it will be G by 1 plus GH, okay, or G by 1 plus G, okay. So this will be density factor ICP KD omega naught by 2 pi SC by 1 plus this can be written as okay. What will be phi ck by phi ck in? 1 by that whole thing, right? So 1 by 1 plus this, which is okay. And what will this be? The last one, phi ck by INCP. Which of the other transfer functions will it resemble? Can you get this easily from the other answers you already have? So this is, I want the output phase divided by INCP. Already calculated phi ck by phi d and phi ck by phi ck in. Is it, which one is it related to? Phi ck by phi d, right? Because I mean, the same current you can represent as an input here after dividing by this gain, right? Is this correct? So this, putting an input here is the same as having an input of INCP divided by whatever gain is preceding that. Okay? Is this fine? So I'll just take this and divide by that whole thing. So times that transfer function. This of course is from the current to the output phase. Okay. So you get some first order transfer functions. Phi ck by phi d is a low pass transfer function with a gain of 1. Phi ck by phi ck in is a high pass transfer function with a high frequency gain of 1. And phi ck by incp is also a low pass transfer function. Okay. Now we have these transfer functions, then what? What good are they? What do we calculate from these? What do you calculate normally using transfer functions? Why do we calculate transfer functions of anything? What's that? I mean, transfer function is output by input. The whole idea is for any output, for any input you can calculate the output. Okay. Now in this case, what does the input mean? So let's consider the first transfer function phi ck by phi d, for instance. Okay. So now this is of course in the S domain. How do we interpret this in the time domain? Let's say, okay, forget this. You have a voltage transfer function, right? So if I have Vi of S, I will get Vo of S. This is in the transform domain. Okay. Of course, in reality, the input signal is a function of time and output signal is another function of time. So what are all the, like, how do I use this transfer function? Okay, I calculate some transfer function in the Laplace domain. What can I do with it? Impulse response. Okay, so that is if the input is an impulse, its output will be h of t. This is usually more difficult to calculate this directly from this input. So usually what you do is you calculate the impulse response as you first calculate the transfer function and then find the inverse Laplace transform, right? Okay. So what else can we calculate? Similarly, you may calculate the step response. If the input is u of t, the output may be some yu of t. So again, typically how do you calculate this? What do you do? You take h of s by s because u of t in the Laplace domain is 1 by s, right? So this you multiply by the transfer function and this you take the inverse Laplace transform. Okay. What other inputs are usually of interest? What kind of inputs do we consider? Ramp, not as common. What? Sinusoids. Okay. Then what? If the inputs are sinusoids, how do we calculate the output? Yeah. So what is this thing? So if the input is let's say Vp cos omega t plus phi naught, what will be the output? Vp times magnitude of at omega. H of what should be the argument here? J omega. Okay, times cos omega t plus phi naught, angle of the transfer function at the same frequency. What is this? Is this the output to this? This is a steady state output. There will be a transient component also. To do that, actually you have to multiply Vp, the Laplace transform of this, right, which will have sine and cosine components, and then you multiply that by h of s and take the inverse Laplace transform. But usually when you have sinusoidal inputs, we are interested in the steady state response and this is what we calculate. Okay. So this is how we end up using the Laplace transform most of the time in practice. From that you calculate the Laplace transform because it's easy. You can get it from algebraic equations instead of setting up differential equations. And from there you can get the impulse response or the step response or the sinusoidal steady state response. You can calculate the output for any input, but this is what we frequently do. Okay. So now this is fine. This kind of makes sense when you have voltage inputs and voltage outputs, right? Step response corresponds to you turn on the input to some DC value and you see what the output is. Similarly, sinusoidal steady state is you connect the sinusoid and then see what the output sinusoid is after some time. Okay. Now what do these things mean? Impulse response and step response and sinusoidal steady state response when you have transfer functions involving phases. What is an impulse here or a step? Sudden change of phase. Yeah, basically the same thing in the phase domain, but again the input will be, so let's say we consider alternating input data. Okay. Something like this. This is data. Okay. Now let's imagine another signal which is going on like this. Okay. The transition instants are the same as this, and let's say for a particular transition it happens earlier, but after that the transition instants are again aligned with the original. This is the first one is the ideal case, and this is another data in which only one of the edges is moved, all the other edges are aligned to the ideal case. So what does it mean in the phase domain? This is an impulse, right? Because essentially if you look at the phase difference between these two, and I will plot it like you would normally plot the sample domain signals. Here it is 0 because they have the same edges, and here this is leading by something, so it has some value, and then again it is all 0. Okay. So this corresponds to a phase impulse. So when you visualize this in the time domain, this is the kind of signal you have to visualize. That is, one of the edges moves a little bit. Okay. So what will be a phase step? So you will start with the edges being aligned, and then this edge advances, and after that all the edges are advanced by the same amount. Okay. Like that, right? So this was the amount of displacement over there. Let's say this is phi p, so that will be phi p. And here similarly I have displacements for same displacements for every edge. Okay. So in this case, if you look at the phase domain signal, if I write it as a sample data signal, it will be like this. And in either case, it will be a step. Okay. It's important to understand, interpret these things. This is a phase step. Okay. What will be a sinusoidal phase? The edges will move back and forth at some frequency, right? So the phase itself will have its own frequency. That is, the edges will move back and forth slowly or rapidly. That is, let's say if alternate edges are, this edge is advanced, next edge is retarded, the next one is advanced, next one is retarded, that is a very high frequency signal, right? Because from sample to sample, the phase is changing polarity. That is like a signal at fs by 2, that is the maximum frequency that is possible. On the other hand, it can be like a whole bunch of edges can be advanced. The amount of advance slowly reduces and the edges become aligned, and then they start going the other way. They start sliding off to the left. So that is like a low frequency phase signal. You understand? So you just have to compare the phase or the transition instance of the actual data to those of the ideal data, and they will vary in some way. That is the phase signal. Okay? So you can have impulses, you can have steps, you can have sinusoids, or whatever we calculate from the transfer functions will relate to these quantities. Okay? Is this fine? Transfer function? I can't hear what you said. What? Ah, yeah, okay. That's right. Yeah. So now let's interpret this further. What kind of transfer function is phi ck by phi d? It's a low pass transfer function with a gain of 1. Okay. What is the bandwidth of the transfer function? This entire thing in the denominator. Okay. So let me just call it in this case, I don't know, omega b or something. Omega naught is probably okay. Okay. So then this transfer function becomes 1 by 1 plus s by omega naught. This becomes s by omega naught by 1 plus s by omega naught. And this is some number times 1 by 1 plus s by omega naught. Okay. So now if I plot the Bode plot of transfer functions, Bode magnitude plot, let's say, if I plot phi ck by phi d, its Bode plot will look like that, right? This is 1, and then here I have omega naught, which is density factor ICP times KD times omega naught divided by 2 pi C. Okay. So this 2 pi here comes from the phase detector gain. Because the denominator has 2 pi, don't assume that this is the cyclic frequency. This is the radian frequency, and if you want the cyclic frequency, you have to further divide that by 2 pi. Okay. So now this has a low pass. This is basically phi ck by phi d, right? This has a low pass transfer function. So what does it mean? What is the interpretation here that it is low pass? What's that? Only slower changes will be? Yeah. So what happens is that if so let's say the edges of phi d start drifting slowly to the left and right. Okay, if it is sinusoidal, it will move slowly, right? So it will move to the, they'll all move to the right and then reach some peak value and then move slowly back to the left. What it means is if this happens slowly over many cycles, this loop will have enough time to correct. Okay, so then this phi ck, which are the edges of the clock here, will also track that. As the edges of the data move to the slide, let's say they keep sliding to the right, the edges of the clock here will also keep sliding to the right because this delay will slowly go on increasing due to the action of this negative feedback. On the other hand, if the edges of the data are moving back and forth very rapidly, what happens is that this won't have enough time to correct for it. So this will be just almost in the same place. It won't move. The edges of the clock won't move. That's the meaning of having a very low transfer function value for phi ck by phi d. That is, let's say you are somewhere here, phi ck by phi d is very small. What does it mean? Even though the edges of data are moving back and forth, the edge of clock is at the same place in absolute time. Okay, that is if you go to very high frequencies, or it moves by very little. Is this okay? So this kind of time domain visualization is very helpful and important, and it makes sense that this this detects the phase, and then that has to charge the capacitor. So let's say it measures the leading phase, it has to charge the capacitor, it will charge it by a little bit, and then it will move the phase by something. That phase may not be exactly what you want, so it may have to move it by further. So if you give it enough time, it will eventually track the input phase. On the other hand, after the first cycle, it corrects it. Let's say this phi d has gone, I mean the edge location has moved rapidly in the other direction, then obviously this tracking will not be correct. Is this okay? So that's the meaning of this low pass stuff. If the edges are drifting around slowly, the clock edge also will drift around along with it. If the edges are drifting, I mean moving around rapidly, jittering rapidly, then it will not be able to follow that. Okay. What is the meaning of this DC gain being 1? What is your interpretation? What's that? Yeah. So let's say you apply a phase step like this. That is, you have the data, and let's say the CDR has locked. The clock edge is in the middle of data. Then you advance all the data edges by a certain amount. That is, one of the data edges moves to the left, and then all of them moves to the left by the same amount. The cycle time is the same after this. Okay. So then what will happen? The output, what will be the step response of this low pass? So if you apply a step here, I will show a continuous time step because we have a continuous time model. So this is the input step, input phase step, right? What will be the output of a system like this, or of a system whose transfer function is this one? It will be exponential. Okay. It will basically do that, and how long it will take depends on omega naught. What is the time constant of this exponential? 1 by, time constant is 1 by omega naught. So the smaller the value of omega naught, the longer time it takes to get there. What it means is that when you apply a phase step, the clock and data recovery starts moving the clock edges also backwards slowly. Okay, in every cycle it moves by a little bit. Okay, and then eventually they will catch up to the data, and then they will again be in the middle of the symbol period. Okay, because finally when it reaches steady state, when this capacitor current is 0, and that will happen only when this clock edge, the rising edge of the clock, is in the middle of the symbol period over there. Okay. So DC gain being 1 means that essentially if you apply a steady phase shift to the clock, that is, or you move all the edges by some amount, all the clock edges also will eventually move by the same amount. Okay. So you can think of other cases like this, right? And this omega naught is this number. Oh, I should not have used omega naught here because I have omega naught there also, right? This is a bad choice of notation. Omega naught I have used for the frequency of the signal. So let's not do that. Let me use omega BW to indicate the bandwidth. Okay. Now the bandwidth, it has all these terms here, df, ICP, kd, omega naught by 2 pi c. Okay. Does it make sense? Why is it proportional to the density factor, transition density? Basically, if you have more transitions, you will have more corrections. Okay, it will get corrected more rapidly. If you have transitions only once in a while, the correction will become very slow. Okay, so it makes sense. Similarly, ICP, if ICP is higher, that means that at every transition you push a lot more current and you push it by a lot more. Okay, the same thing goes for this KD, the gain of the delay. That is, for every unit change in control voltage, the delay changes by a lot. So that means that the correction applied is a lot, and this exponential here will build up more rapidly. Okay, so those things also make sense. Okay, so one thing to realize here is that the bandwidth, this is in general true of any clock and data recovery system, is proportional to the transition density, and this makes sense. I mean, if you have no transitions, you have no information to correct it, so you have to wait for the next transition to correct it, and it takes a longer time. Okay, and as I emphasized repeatedly, the transition density for random data is half. Okay. So this is how, I mean, you have to now decide like what bandwidth you want. Having very high bandwidth will have some disadvantages, having very low bandwidth will have some other disadvantages, and so on. So based on that you have to decide. Okay. Is this fine? So similarly, if I plot let's say phi ck by phi ck in, what will that look like? Band first, high pass. So it will be just a complementary curve to this, right? And it will have the same corner also. And this has a high frequency gain of 1 and some corner like this. Now why does this make sense, this being high pass? If you look at this, what happens? High frequency? Yeah, so basically if this clock in is, let's say, varying slowly, so initially what will happen is this moves, let's say this clock in, the edge moves to the right, this edge also will move to the right by the same amount. Okay, but then in the next cycle the phase detector will sense that phase difference and correct it. So if this clock in is moving slowly, it can correct this clock, it will be brought back to the middle of the data period. Okay, so that's the meaning of. Now what is the DC gain of this function phi ck by phi ck in? What is the DC gain? 0. So what it means is that if you, let's say this clock in, at some point all the edges are pushed to the right by some amount, or left to the right by the same amount. Okay, so then what happens is initially there will be some phase difference, but eventually it will get corrected. Okay, so what happens is eventually the delay will adjust itself so that this clock will be in the middle of the data. Okay, so that means that although this clock has moved, this doesn't move at all. Eventually the steady state gain will be 0. On the other hand, this is varying rapidly, it cannot be tracked, and you will have whatever variation you have in clock in will appear there. That's the meaning of the high frequency gain being 1. Okay, so just think about these things. I mean, in general, like as you go to more and more advanced stuff, one thing is to analyze it. This analysis is trivial, right? This is just first order transfer function. More important thing is to interpret what the transfer functions mean. Okay, and then we also have the what is the transfer function from the charge pump noise to the output. It will have a low pass function, and that's whatever it is. So that will essentially enable you to decide the size of the charge pump, size meaning the current of the charge pump and so on. Okay. So there are many performance metrics. First of all, what is the quantity that decides whether the clock and data recovery circuit, the output clock of the clock and data recovery circuit is tracking the data correctly? What quantity would you look at? Huh? 5d minus 5ck, right? 5d minus 5ck should be ideally 0. So that by our definition means that the clock rising edge is in the center of the data symbol. Okay. So you can look at what happens to 5d minus 5ck under different circumstances. So that is one measure, that is how well you are tracking the data in spite of some changes in the input. Okay. Another measure is you recover this clock, and this recovered clock can have some jitter. I mean, it may be desirable because if the input data has jitter, this has to also have jitter so that it will follow it. On the other hand, you also use this recovered clock in the rest of the signal processing. Okay. So maybe you use this to retransmit. Again, these things will become a lot more important when you don't have the forwarded clock. Okay. Because when you have clock from the other side, you could also pass it on to the following stages. But when you don't have forwarded clock, you are regenerating from that. So the jitter in the output clock becomes important. Okay. And also one more thing is, let's say the input data doesn't have any jitter, the input clock doesn't have any jitter, right? So this data is like clean, and this clock is also clean, that is, there is no jitter at all. What do you expect for this? Will it have jitter? It will have, first of all, two things. One is, of course, it will have random jitter because of random noise of the charge pump. Okay. There may be some noise due to the phase detector also, but mainly the charge pump is what is important. Charge pump, and also one more thing is, I mean, this delay. The delay itself will not be, will have noise because, I mean, you can imagine, that is, how do you make a delay? You make a delay using, let's say, some inverters, and then you have some input. When the input crosses some threshold, the output starts rising, and then you will have a delay. Okay. Now there will be some input referred noise. Okay. So this instant at which it crosses the threshold is also influenced by input referred noise of this. So the noise of these stages will cause a jitter, right? That is, even if the input doesn't have any jitter, the output will have jitter. Or if you make ensemble of thousands of, I mean, many of these instances, and then apply the same input, the output edges will all be at slightly different times because of the internal noise. Okay. So that also adds essentially something like phase noise or jitter to this, and that can be modeled by adding a noise over here. Okay. That is the phase noise of the delay line. Okay. So now, so this means that even if the input data and clock are clean, the output will not be clean. Okay. So you have to calculate, this is known as jitter generation. This is internally generated jitter. Okay. Even if the input is, this is like the circuit noise, right? If the input is 0, the output will not be 0 because of noise. Okay. So that's what you will get here. Also, there is one more thing which we know from the operation of this phase detector. We know that the output of this charge pump, the average value is the phase difference divided by 2 pi times ICP. Okay. But in addition to that, you will have pulses, right? You will have this up minus down, that pulsing waveform. Okay. So you will have an additional error here. This is basically the charge pump pulse, right? So this is in general true of every phase detector. The average output of the phase detector follows the phase difference, but in addition to that, there will be some periodic error, some jumping of signal back and forth. So now this also causes similarly periodic error in the some changes in the output phase. Okay. So this is not so important with the linear phase detector, but with other kinds of phase detectors it will become important, as we will see in the bag-max phase detector and so on. Is this okay? So this is to motivate, first of all, to derive the phase domain model, and then there is a need for it. I mean, we don't do it for the sake of doing it, right? Because we want to answer questions like, if we design this, first of all, as a designer, you want to know how big ICP should be, how big C should be, and so on. So now you know from the expressions that these will decide the bandwidth, that is, up to what frequency will the clock track the data. Okay. So if you decide to, let's say, be cheap and use a very small ICP, then the bandwidth will be small and you cannot track high frequency jitter. And you also want to have some measure of how well the clock is tracking the data, and that's given by phi d minus phi ck, and there will be some metrics related to that. And on top of it, anytime you make a circuit, it will have its own noise that you can get from looking at the noise of the charge pump as well as the phase noise of the delay line and computing the transfer function to the output. Okay, this is fine. So we will look at these things and the associated metrics. There are some standard metrics for clock and data recovery circuits that are used widely. There are some measurements that you will have to make. If you make a clock recovery circuit, people will expect that you make these measurements and show them as specifications. Okay, so those things we will discuss. You can, right? I mean, if this TD is only discretely variable, then it may also model that. Okay. On the other hand, I mean, if you do have, it depends on how you make the delay line. So let's say you make an inverter chain and vary the supply. Okay, so in this case, the delay will be very continuously. Of course, you cannot go below a certain value in a given process, but it does very continuously. Any questions about this, about the phase model or the interpretation? It's very easy, especially with the CDR with the forwarded clock. We have a first order transfer function. But like I said, the derivation of this is trivial, right? I mean, once we have the model, getting the model is important. After that, getting the transfer functions is quite easy. Then again, more significant step is to interpret the transfer functions. What kind of transfer function will you have from the delay line noise to the output? It will be high pass. So what is the intuition there? So it's the same thing. I mean, if the noise of this is slow, right, then the feedback loop will correct for it. So let's say if because of noise this delay tends to increase, then the feedback loop will decrease the control voltage, so that, or rather increase the control voltage so that the delay reduces and it compensates for the noise. Okay. But if again you have high frequency noise in the high frequency phase noise in the delay line, I mean, you cannot do anything to correct it because it takes some time for the loop to correct that one. Okay. This is fine. So this is a phase domain model, and we will make this kind of model for any clock and data recovery circuit that we make, or other similar circuits like the phase lock loop. Okay. One for alternating data. Yeah. There is no data. Okay. Any questions? Okay.